All right, in this problem, we're going to find the limit of what looks sort of like a pretty crazy looking function, or a function that I could not sketch the graph quickly, I don't think. So how am I going to find this limit? Well, what I'm going to use is the Squeeze theorem, or also known as the sandwich theorem. They're saying prove this or show this. Show that this limit is equal to 0, or prove this limit is equal to 0. So this is a proof. What you do with the sandwich theorem or the squeeze theorem is we compare our very involved, complicated looking function, we compare it to an easy or familiar function, a more elementary function. We have these elementary functions that we have from pre-calculus. So sometimes people call it the squeeze theorem, other times the sandwich theorem. Now, the first thing we do is we build an inequality, the sandwich. We build, maybe build's not the right word, but that's what I wrote down. That's what I said. But we can build or construct an inequality, and when I see cosine or sine, that's where I can start in the inequality, because cosine, same is true of sine, regardless of what I put inside, has a maximum value of 1 and a minimum of -1. Cosine and sine are always bound by -1 and 1, right? And what I mean inside is that here the input for this cosine argument is, the input argument for the cosine function is 2 over x. But if I don't even think of what's the argument that I'm putting into the cosine function, cosine is still between -1 and 1. This is the starting point for an inequality that I can use for the squeeze theorem. All right? Okay, now I'm sort of getting there. My function is not cosine 2 over x. I don't think that limit exists anyway, so pretty sure if I just had that function, the limit wouldn't exist. But if I multiply by x to the 4th, well, that's what I need. I need to multiply by x to the 4th. So I'm going to multiply through now, keep in mind that x to the 4th is always positive for x not equal to 0. So you put -1 to the 4th, -5 to the 4th, those are all positive. 5 to the 4th positive. Why would I mention that? Because when I multiply an inequality by a number or variable, if that number is negative, it's going to flip the direction of the inequality. But we don't have to deal with that because x to the 4th is never negative. Okay, so it's non-negative. I can just multiply that through without worrying about changing the direction of the inequality. It's a little detail that I could have gotten away with not even mentioning, because if you didn't think about it, you'd still get it right. All right, see now, x to the 4th cosine 2 over x is bounded by these two functions. And this cosine function, this cosine 2 over x, is going to do some funny things. So it's not as, I don't know, I just want to hopefully can appreciate that cosine 2 over x is as a function that, roughly speaking, I'm going to erase this, but it's going to oscillate infinitely as it gets closer and closer to 0. This is something what cosine 2 over x looks like. Something like that. The limit's not going to exist. It's a crazy looking function. I mean, the graph. Crazy? That's just not very precise, so maybe I shouldn't use that in math. I'm just saying that it is not something that an elementary function, this composition of cosine 2 over x, that is not something that elementary function that you might have studied in pre-calculus. It's a 2 over x is simple, or an elementary function, cosine elementary function. The composition makes something more involved. Now, but we're comparing it to x to the fourth, which is a polynomial, and those are functions which we can easily find the limit. I just plug in 0, and I get the limit of that outside function is equal to 0. X to the fourth, that limit's equal to 0 fourth is equal to 0. So these two outside functions have a limit equals 0. By the way, just by starting off, you do not know that middle function, the middle guy being x to the fourth cosine 2x, we don't know that limit exists. I mean, when you just by giving some function, we don't know the limit exists. So I see people, students, putting limit in front of these. See, what they do is they say, okay, I'll just put a limit in front of these, like that. And this one's equal to 0, this one's equal to 0, the middle one's equal to 0. That is 100% wrong, because we don't know that the limit in the middle exists. That's not using the squeeze theorem. That's using another theorem that says if we know the limit exists and one function is greater than another function, then the limits have that same inequality. It just drives me crazy, because I don't know where people get that from, why they're doing that, because that is wrong. All right? So the squeeze theorem says that we're starting off, and suppose we don't know that middle function exists, and I don't have really a strong reason necessary to think that middle function exists. Well, we have to prove it. That's sort of what we're doing here. So, I mean, not sort of, that's exactly what we're doing. So x to the fourth, those limits are 0. So then we conclude, therefore, because the outside functions have limit 0, the inside function, the one that's sandwiched in between or squeezed in between those two x to the fourth, those are equal to 0. And we should say why? By the squeeze theorem. That ends the proof. By the way, since I don't have a computer doing this, I'm going to just sort of roughly sort of take a guess of what this is going to look like. But an educated guess, because there's another problem that's similar that has sine that I've looked at. It's almost the same problem, really. So if you look at what's happening, is you have on the top I'm not drawing a very good picture or sketch of this, but x to the fourth roughly looks like a parabola, very roughly. It looks more like more of a U shape. But anyway, I have y equals x to the fourth on the top and negative x to the fourth on the bottom. And what's going on is that this cosine graph is getting squeezed in between. And it's because of the way it's not cosine of 2 times x or x over 2, it's 2 over x, the thing starts oscillating. That's a whole other story of how that works out. But it's oscillating, but the x to the fourth acts like sort of like a magnitude of a cosine function, and that magnitude approaches 0. So it's getting squeezed in between. That's really roughly what the graph looks like for this function. It's getting squeezed in between the green x to the fourth and negative x to the fourth. I could have done those x to the fourth a little better also. They're really more coming up more like that or something. But anyway, okay, that's a little extra. And I didn't try as hard. I didn't look up on a computer program trying to find a good picture of that. But okay, so let's just leave that for a while and just focus on this, and we'll have that the last thing we see on the screen before the video ends. Recap, how do we prove something using a theorem? The theorem has two parts in the hypothesis. One is that you have an inequality, which I put a little bullet there. So we need to build that inequality. The second part of the hypothesis is that the limit of the two outside functions are equal to each other, in this case 0. And then, so we could call out, those are our hypothesis. And then this is right here, the conclusion at the end. It would be better if I wrote it like that. Actually, I don't know if I have enough space here. But if I could write, this is the, maybe I'll just write here, conclusion. I have the therefore, and then up here, we could say, this would be our hypothesis. Well, I'm not gonna write that, but we have those two things satisfy the hypothesis, and then the full third point is that we come to the conclusion, our therefore. So the first two through bullets are satisfying the if portion of the squeeze theorem, the last one, the conclusion. Okay, that was a lot of talking, but there we have the squeeze theorem applied to this limit problem.